So we're looking at the situation where an object is thrown down. And in this case, we're going to look at a situation where it's thrown down at a speed greater than the terminal velocity. Now, there's three situations when you throw an object down. It could be thrown down at a speed that equals the terminal velocity. Well, then it's just going to be at that constant speed the whole trip. It could be thrown at a speed that's greater than the terminal velocity, or it could be thrown at a speed that's less than the terminal velocity. So let's look at this one where it says the object is thrown down with initial speed twice the terminal velocity. And later on in the question here, they refer to the terminal velocity as v subscript capital T. So they're basically saying it's twice vt is what it's thrown down at, whatever vt is. It says take gravity as g, as always, I guess, and air resistance as proportional to the square of its speed. So the air resistance is something like kv squared. It's going to be against it. And unless, I guess, told otherwise, this is going to have some effect on the mass. So we get be affected by the mass of the object. So the way that this question's gone about it, making that clear is in part one, because we're not dividing by m here. So the force isn't just minus kv squared, but the force is m times minus kv squared. All right, so we need to show that this is the situation here as the first part of our question. So the mass times the acceleration of the object is equal to, and here's the forces, mg, and I'm going to take going downwards as positive, and that makes sense because everything that's happening in this question is going downwards. The object was thrown downwards. So downwards is positive, which means this resistance force, m times the kv squared, is acting in the opposite direction to the gravity. The air resistance is acting upwards on the body as it's trying to fall down. So I can divide by m here and get y double dot is equal to g minus kv squared. And I get what they're wanting there. But I think that's their way of just making sure you realise to times that by m. All right, the second part, find the terminal velocity. Well, when you reach terminal velocity, the net force on the object is 0, and then you're at your constant velocity. So that means the acceleration will be 0. So if we put 0 in here, we'll get g minus kv squared. So kv squared equals g. So v squared equals g on k, which means I can squeeze this in. V equals root g on k. Terminal velocity, v equals root g on k, found by putting the acceleration equal to 0. Last part of the question is going to take a little bit longer because we're going to find the time taken for the object to reduce its speed from twice the terminal velocity that it was thrown down at to 1.1 times the terminal velocity. How long is that going to take? So really, I need a time equation, right? And fortunately, I guess it's a time equation in terms of velocity. So if that's the case, I think I need to treat this acceleration as dv dt. So dv dt is equal to g minus k v squared. Now I need to do my integration. So I'm going to separate out. I've got dv on g minus kv squared equals dt. And I'm looking ahead at this and I'm thinking I've got a quadratic on the bottom, which I could make b the difference of two squares, and then I could use partial fractions in order to integrate. So let me first maybe divide out by k. So I've got dv on k times g on k minus v squared. So I'm just pulling k out of there, and that's equal to dt. So then that means I've got, if I multiply by k over this to this side, multiply both sides by k, I get rid of this one that's been divided by k. And then here on the bottom, I've just got what's in these brackets, and that's root of g on k is being squared minus v squared, the difference of two squares. Move along a little bit here, and I'll work in this little section here. So going from here up to here, what I'm going to try and do now is express this as partial fractions. So I'm saying that 1 on this root g on k squared minus v squared is equal to a on root g on k minus v plus b on root g on k plus v. Because I factorised that into linear factors, and now I need to work out my a's and b's there. So I'll just multiply up and get 1 is equal to a times root g on k plus v plus b times root g on k minus v. Right, if I multiply everything by what's on the bottom there. Okay, and then I can choose appropriate values for v in order to figure out what a and b are. Like I can let v equal minus root g on k. Well, if I do that, root g on k minus root g on k, nothing, so that gets rid of that term. And if I've got root g on k minus root g on k, I actually end up with 2 root g's on k's in that last set of brackets. So I'll get 1 equals b times 2 root g on k, if that's the case. So b is equal to 1 on 2 root g on k. So b is equal to root k on 2 root g. b is equal to root k on 2 root g. And I can do the same thing. I can let v equal root g on k. Well, if that's the case, root g on k minus root g on k is 0, and that just cancels away. And root g on k plus root g on k is 2 root g on k's. So I'm going to get 1 is equal to a times 2 root g on k's. But that's the same situation as here. So that's just going to bring me down to a also equaling root k on 2 root g. So I know my values of a and b here for when I want to go and integrate. All right, so let's get a bit of room here. I'm trying to find, I've got the integral of, and it's a is root k on 2 root g, a on root g on k minus v, plus, and I've got b, which is root k on 2 root g, on root g on k plus v. So all that dv, I just need to go back slightly so you can see what I've got written there. So that's my a on my linear factor and my b on my linear factor dv. And that's my integral sign there next to it is equal to the integral of, and over here it says k dt. All right, so these aren't too bad to integrate because that'll just be to do with natural logs. I need a minus 1 on the top and I need a plus 1 on the top. So this would be minus root k on 2 root g, natural log of root g on k minus v. And this will be root k on 2 root g, natural log of root g on k plus v. And this will equal kt plus some constant of integration. Before I go any further, just want to point out that it was thrown down with velocity twice the terminal velocity, and then it encounters air resistance as it's heading down. So it's only getting slower and slower and slower. So then the initial throwdown. So whatever happens, it gets slower and slower until it reaches terminal velocity. So thrown down at twice terminal velocity slows down to terminal velocity. We found a terminal velocity before was root g on k. We did. So that's the terminal velocity minus whatever its velocity is, which we know is going to be greater than the terminal velocity. So this is negative, right? So technically, what I should have been doing is I should have been putting these absolute values around my integrations of my logs, right? But this one's positive, so I don't need to worry about that one. And if this definitely is negative, then I can just swap these guys around and it's sorted. That'll be like taking the negative of it, which is what the absolute value signs will do for me. So that's what I'm going to do here. I'm just going to write one more line of working in here. 2 root g natural log of v minus root g on k plus root k 2 root g natural log of root g on k plus v equals kt plus c. Just to take care of any negative values in there in the logs. So we're right to go now. I can put these logs together. They've both got the same coefficient. That's great. So it's like it's this one minus this one. And when you do a log minus a log, it can go inside together as the division. So I'm going to grab their coefficient and natural log, and this one, root g on k plus v, divided by this one, v minus root g on k. And then that's equal to kt plus c. So it'd be nice to figure out what c is. Well, we know some initial conditions. We know when t equals 0, we've got twice the terminal velocity. So when t equals 0, v equals 2 vt, which is 2, and we know the terminal velocity is root g on k. So I'm going to pop that into the equation I just found. All right, I've got root k 2 root g natural log of root g on k plus v. So plus 2 root g on k, because our velocity is twice the terminal velocity at time 0, on v, which is 2 root g on k, minus root g on k. So that's the log bit. equals k times 0 plus c. So c is equal to this, but this can be simplified. There's 3 of them on the top line and 1 of them on the bottom line, isn't there? 1 of those plus 2 of those is 3 root g on k's, and 2 of those minus 1 of them is just 1. So this is root k on 2g, root g, natural log of 3 of them on 1 of them. It's just the natural log of 3. And that's equal to c. So let's write down what our equation is at the moment involving velocity and time. It's root k on 2 root g, natural log of root g on k plus v on v minus root g on k equals kt plus c, which is root k on 2 root g, natural log of 3. All right, so let's subtract this off both sides. And when we subtract logarithms, because they're going to have the same coefficient, when we subtract this off this side, if you subtract logarithms, then you are actually dividing. So we've got root k on 2 root g, and we've got our ln root g on k plus v on v minus root g on k. And what we're going to do is subtract off this other ln3. So we'll have to do a division in the next round, and that's kt. Okay, so I should probably divide by k as well at this point. So if I divide by k, this will be like 1 on 2 root kg, because root k divided by k is 1 on root k, and I've already got a root, so that'll be that for there. And this is the natural log of, and I divide by 3, so it's this divided by 3. So it's the natural log of root g on k plus v on v minus root g on k, but this is times by 3 in there because it's divided by 3, and that's just equal to t. So I've got an equation for time in terms, time equals this in terms of velocity, and I can answer the question, how long did it take to go from twice the terminal velocity, which is what we threw it down with in the first place, so at time 0, to 11/10ths of the terminal velocity, which it said in the original question, or 1.1 times the terminal velocity. So basically they're saying, I want you to put 1.1 times the terminal velocity in there for v. And we know the terminal velocity is root g on k. So we've got to put 1.1 times root g on k in there for v. So let's see if we've got enough space on the board left here to get this one done. We're running out of room, but we can get there. So our equation is 1 on 2 root k times g, natural log of root g on k plus v, and then on 3 times v minus root g on k, which is equal to t. So that's our equation there that we're working with, but instead of v, we're putting in 11/10ths of the terminal velocity, 11/10ths of vt, like the question said. So that's, we're putting in 1.1, 11/10ths of the terminal velocity, which is root g on k. And here we're putting in 1.1 root g on k. So our answer to our question, how long is it going to take to go from being thrown at twice the terminal velocity to slow itself down to 1.1 times the terminal velocity will be 1 on 2 root kg, the natural log of, and we need to figure out what this is. Well, we got one of these plus 1.1 of them in. So we've got 2.1 of these root g on k's all over 3 times, and 1.1 of them minus 1 of them is 0.1 of these root g on k's. All right, so 2.1 of them, and what's 3 times 0.1? Well, 0.3, so I can change that to 0.3, and these will cancel, and what's 2.1 on 0.3? Well, that's the same as 21 on 3, that's 7. So my answer is that t is 1 on 2 root kg, natural log of 7. 1 on 2 root kg, the natural log of 7. That's how long it takes. And how long do you reckon it would take to get to the terminal velocity? Well, you just need to, instead of putting 1.1 in there, you'd need to put in there just the terminal velocity. So if I did that, what happens? That's an interesting thing, isn't it? If I do that, because I remove my 1.1, I actually get it just subtracts off that number. And that would be 0, but then you're in trouble. Now, why does that happen? That's right. It happens because it approaches the terminal velocity but never actually gets there. So I wonder if you could think of a way to work out how long it would take to get to the actual terminal velocity, because we can't do it by substituting it in this way. Well, that's right. It takes an infinite amount of time. So it never actually gets there. It just gets closer and closer and closer and closer to it. So it's going to depend on what your level of how close you want to be.